Good morning. Welcome to the morning session. There are 3 talks today in the morning, and I invite Professor Morita to chair this session.
Thank you very much. So today's first talk is Pietro Corvaja's second lecture on the bounded generation of linear groups and Diophantine approximations. So please.
Thank you. I'll start with recalling the theorem proved in collaboration with Andrei Rapinchuk. Jim Boren, Umberto Zanner, says the following: gamma is a linear group characteristic of K equals 0, and gamma is boundedly generated by semi-simple elements, so that form where gamma I semi-simple then gamma is virtually abelian. The proof of this theorem involves Diophantine approximation and the theory of exponential Diophantine equations. So this talk will be devoted to developing both the link between this statement and the theory of Diophantine equations and the arithmetic theory needed to prove this theorem. But before going on, I'd like to mention a companion result in positive characteristics. This is due to Aber, Lubovsky, and Piba, which says that if characteristic A is positive, every bounded generation linear group is virtually solvable. It's virtually abelian. So even stronger. Anyway, I will concentrate on characteristic 0, and the first topic today concerns linear recurrent sequences. These are sequences of, let's say, complex numbers, since we are working in characteristic 0, satisfying following relation for certain coefficients, that un plus d equals a1 u n plus d minus 1 plus secant ad un, and we also assume ad different from 0. Of course, any such sequence is uniquely determined by its first d terms, u0, u1 up to ud minus 1, and then the recurrence relations. Recurrence relations gives all the other terms. And the most famous one is Fibonacci. Fibonacci sequence. This term are called, denoted by Fn. So satisfies Fn plus 2 equals Fn plus 1 plus Fn. And the initial terms f0 equals 0, f1 equals 1. And there is also another fundamental example, which is the trivial sequence 0, 1, 2, 3, 4, 5. Yes. Sequence. And here each term is the arithmetic mean of the preceding term and following one. So it satisfies the relation 1 up un plus 2, which means that un plus 2 equals twice un plus 1 minus un. Okay, so all linear recurrent sequences of order D of any order become recurrent sequences of first order if viewed as transformed into sequences of vectors. For instance, if one defines the Fibonacci vectors Vn made of 2 consecutive Fibonacci numbers, then Vn plus 1 equals metric associated to the recurrence multiplied by Vn. And this implies that Vn is the nth power, that matrix multiplied by the initial vector 0, 1. And now the matrix, Fibonacci matrix, is diagonalizable and its conjugate to matrix phi 0 phi tilde, where phi is equal to the mean and phi tilde is its Galois conjugate. And from this one can obtain the formula for the nth Fibonacci number. To a linear, to the recurrence sequence, the recurrence relation, we associate the characteristic polynomial which is x to the d minus 1, a1 x to the d minus 1, ad. Note that Fibonacci case, but actually in every case, Px is the characteristic polynomial of the associated matrix. in the case of arithmetic sequence, the companion matrix is which is conjugate to, and actually we have this well-known formula. So we obtain polynomial instead of powers. And in general, a very linear recurrent sequence admits expression of the 4 UN equal sum J1 K Bj n lambda J dn, where lambda 1, lambda K are the roots of the characteristic polynomial, and the coefficients are polynomial of degree strictly less than the multiplicity of lambda J as a root of capital. So in other words, when the companion matrix is diagonalizable, all the coefficients are constant. There are as many roots, as many eigenvalues as D, as the degree of polynomial P. So this degree is 0, and we have an combination of exponential function expressing expressing UN. Otherwise, we can have polynomial coefficients. Here, the eigenvalues is 1 with multiplicity 2, and so we have polynomial of degree strictly less than 2, which turns out to be 1. And from this, it follows that whenever A is a D cross D invertible matrix, then the power A to the n are given by ij n. Well, for each ij, the sequence A sequence and the n to ij of n is a linear recurrent sequence. And satisfying the recurrence relation associated to the characteristic polynomial determinant plus 1. Of course, some coefficient might also satisfy a shorter relation. For instance, here we have two coefficients which are always equal to 1, and one which is 0 constant. And so I think we start to see the relations between problem of parametrizing a group in this sense. If you write 1 to the n1, k to the nk, this is matrix ij k, and these functions have the property that they are linear recurrent in each variable, fixing all the others. And it turns out that they are what I call exponential polynomials. In k variables. So it can always be written as sum for k one to, let's say, t of certain polynomial f I k x1 xk multiplied by certain number lambda. We can write it as lambda k, lambda 1. We can, well, I'll explain in a moment. So linear for xk where lambda 1, lambda t is a generator set for all the involved roots. The roots of all the characteristic polynomial and Li, J, K are linear for. No, 1. Okay, so actually, well, this is so this is what we call exponential polynomial parametrization. And if each gamma I is semi-simple, then each gamma I is semi-simple, then the polynomials are constant. And actually, we call it purely exponential parameterization. Actually, so we are reduced to studying groups which are parameterized by purely polynomial maps. And now I'd like to introduce the tools from the Diophantine approximation. I start with rough theorem. It states, well, it's back to the 50, I think. Says that if alpha is a real algebraic number, and epsilon is positive, then there are only finitely many rational numbers, p over q. Here, q are integers, q prime, q positive, such that the distance, the approximation of alpha by p over q is less than 1 to the 2 plus epsilon. So better than what is what can always be done by an argument based on pigeonhole principle, the Dirichlet lemma. And actually, this inequality can be written in more homogeneous form, multiplying by q squared. So it can be written as q alpha minus p divided by q less than 1 over q the epsilon. So we have on the left-hand side, we have the product of two linearly independent linear forms in QP. So the linear, say that PQ will be Y. So here we have Q Y alpha minus X and Y linearly independent linear form. And if, for instance, alpha is less than 1, is suppose that alpha is between 0 and 1, then Q will be larger than P, at least for all but finitely many solutions of this inequality. And so Q will also be the maximum Q and P, which is the height of the point, the projective point QP. Whenever Q and P are co-prime integers, you can use this as the definition of height. So for the moment, it's a definition. So here you have product of two linearly independent linear forms at integral points is less than the height of the point PQ minus epsilon. And one can also rewrite this inequality in an even more homogeneous form, so that it will not depend on the projective coordinates used for the projective point QP, so that it's independent by a multiplication by a scalar. So we can write again maximum QP. Yes. And Q multiplied by the maximum of QP. And since I divided twice by the height, I obtain again the height minus 2 minus 5. So this quantity are independent on the projective coordinates, and they can be viewed as distances. The first case, PQ from the point alpha 1, with projective point alpha 1, or the affine point alpha, and here the point at infinity, the point 1, 0. So this is linear forms which vanishes at the point 1, 0. So it is small, this quantity is small whenever the point PQ is close to the infinity. And this formulation suggests its extension in higher dimensions, which is the so-called subspace theorem. So the subspace theorem concerns approximations of a family of hyperplanes in projective plane, in projective spaces by rational points. And for this, I must introduce a notation. So K is a number field. S is a finite set of evaluations. Okay, do not suppose that S contains all the Archimedean ones. So we fix the dimension, let's say n, that's a number. So we consider for point x0, xn, projective space, threshold point. So its height is the product over B. We say dk is the set of all valuations, okay, all places, so classes valuation, the maximum of 0, and where the absolute values are normalized so that product formula holds. We have seen in previous talk that one can normalize, so taking if P divides P, this is usual periodic absolute value to the quotient. And accordingly, if V is an infinite, take the complex absolute value so the local degree, well, again, KB over R. Yes, local degree over Q. As it will appear later. It's connected with the subspace theorem, not with the definition. Okay, and so this is the definition of height, and now the subspace theorem, which is due to Schmidt in particular, but crucial case, and Schlickeweil in the general case, says the following. For every V in S, choose linearly independent linear forms L0, Ln in X0, Xn. And inequality, the solutions X0, Xn in projective space, that's rational over K, to the inequality product over V, product over I, 0 to N, the absolute value of L. So this depends also on, for every V, we have this uniforms of X V over the maximum X 0, 0 V X and E less than the height, the minus n minus 1 minus epsilon. So here n equals 1. Lie in a finite union of linear proper linear subspaces. And in the case of Roth theorem for dimension 1, the subspaces of P1 are just single points. So we have finiteness. Here, finiteness does not hold in general. So you see, this is a measure of the approximation of the rational point X to the hyperplane where the form Li vanishes. So it says that given a configuration of hyperplanes, cannot go too close with respect to different valuations. And let's see. Consequence of this theorem, fundamental one, the only one where we'll be interested is the S-unit equation theorem. This was proved by Aleksy and independently van der Poorten and Schlickeberg. After preliminary work by Dubois and Rhin. And in dimension 1, it is a theorem of Siegel and Mahler, and it says the following. So consider equation x1 plus xn equals 1. Equation to be solved in S units. So here in this theorem, S contains the Archimedean absolute values. So that one can define the ring of S integers. And its group of units. Be solved in S units. That's only finitely many solutions such that no subsum vanishes. Of course, you can have xn equals 1, and for instance, x2 equals minus x1, so it's eliminated. And I'd like just to show how Roth theorem gives this result. Well, the generalization of Roth theorem Roth theorem with periodic valuations. So we take the subspace theorem dimension 1, and it differs from Roth theorem because here we allow several valuations, while in Roth theorem we had only the usual absolute values. For instance, it gives finiteness. Solutions of a Diophantine equation of the form 2 to the a minus 3 to the b equals constant. So let's see how we can work. We can consider projective point 2 to the a, 3 to the b. Then S will be consist of usual absolute value and quadratic and triadic. And now, what does the linear forms for mu equals infinity? So suppose, for instance, this is positive, so 2 to the a is larger than 3 to the b. We consider y as y. 1 infinity is the difference, x minus y. So for quadratic absolute values and for triadic absolute values, we take L0 equals x, L1 equals y. So if you make the product, yeah, it's to that y over the maximum in the absolute values 2 to the a multiplied by x minus y. And here we have the maximum in the quadratic and triadic absolute values is 1 in both cases. So we have 2 to the minus a and then 1 and 1 and 3 to the minus b. And here, well, here it's y is 2 to 3 to the b, and this is the constant. So we have this cancels out. And so we obtain 2 to the 3 to the minus 3a, which is the height to the minus 3. So it's less than height to minus 2 and, well, this constant. Minus epsilon for epsilon equals, let's say, 1/2. So we obtain finiteness. And this proof generalizes to general case. And I'd like to show why we cannot have finiteness in general. So consider consider the following case, S-unit equation in 3 variables. So we have this equation. And the S-unit solutions correspond to the integral points on the complement in P2 of 4 lines in general position. So a configuration of four lines in general position. Let's see why. If one of the line is the line at infinity, so we have the P2 minus line at infinity, this is A2, and the integral points are just OS cross OS. So pairs XY of S integers. Now, if two of the lines are x equals 0 and y equals 0, the ring of regular functions on this variety contains the function 1 over x, because it has no poles after removing that line, and 1 over y. So we also want that x be an S unit and y be an S unit. And finally, if the fourth line is the line defined by the vanishing of the sum x plus y. Well, suppose that's x. So these are homogeneous coordinates, x plus y plus z equals 0. Then we want that the sum, let's use homogeneous coordinates. No, I'm for the moment, I'm proving this assertion that yes, you need solutions correspond to integral points in this open variety. So it's no. The subspace theorem says that well, the yes unit equation theorem says that all but finitely many. Yes. But I want to give a geometric interpretation of this result. So we can suppose that in homogeneous coordinate, this is minus, sorry. So that this is one of the other lines that to be removed. Then it means that x plus y plus y minus 1 should be invertible. So this must also be a unit. And so finally, we obtain that equation, and which are the degenerate solutions. Degenerate solutions are, well, there might be finitely many solutions, and then you see this these three dotted lines. What is it? Where is the third? Correspond to varieties of the form P1 minus 2 points. And this is isomorphic to GM. So there is an embedding of GM embeds into this variety. And GM of OS star. And so we can have infinitely many solutions to this equation, but all but finitely many lies in these three families. And these three families can be seen from the equations. The families x plus y equals 0, z equals 1, and then x plus z equals 0, y equals 1, and z plus y equals 0. So the distribution of integral points on this on this affine surface is that. So you have a finite set plus 3 infinite families. And this is the reason why the subspaces arise in the subspace theorem. So that's all for today. And thank you for your attention.
Thank you very much. Are there any questions or comments?
Yes, next lecture. In bounded generation, by semi-simple elements, we have to work with exponential polynomials. And the exponential polynomials, when evaluated at integers, are a linear combination of S units for a fixed S. Because we have an expression of the form of Aij constant times expression of this form. And if we enlarge S so that all these are S units, then this is a linear combination of S units like this. And so we have to work with linear equations in S units. Well, the ring of regular functions is the ring generated by x, y, 1 over x, 1 over y, and 1 over x plus y plus 1. So when you homogenize it, so all this must be inverted. This quantity must be inverted.
Other questions or comments? Okay, let's thank the speaker again.
Thank you.